Hello and welcome everybody for today's AI for Earth 2 final presentation. We will be covering two different challenges today that the lovely Footprints members and participants tackled this year for several organizations. So we'll be covering those as well. But first of all, of course, are the people from the AI for Inland Floods, where we also had a team from Xomnia helping us out, and the AI for Forest Health people that combine their efforts into some final results, which they will tell about themselves. But let me first just give you guys a brief introduction of what we're going to do today. So we will have a bunch of presentations. I'll just give you a short introduction about how we do these challenges for those that are external today, but I'll try to keep it short. Then we go to the exciting stuff. Pavlos is going to present the Inland Flood Team 1, and Flin is going to present for his Team 2 about the results that they gained in flood prediction. Then Vortex also has the opportunity to give some final words and on the challenge and how they are going to implement it into the real world, because of course that's why we're here, trying to make some impact. Then Julieta will give the presentation for the forest health theme, and there as well we have some closing words from the forest radar side to see how they will be using these results as well. So that is what is up for the program today. But in short, just for everybody that has never heard this story, we are Footprints, we are the global AI for Good community, and we aim to solve humanity's greatest challenges by educating AI engineers at scale with an ethical and sustainable mindset. The way we do this is we do AI for Good challenges. I can tell you all about different examples, but you'll hear all the different, several different examples today in this presentation. So I won't bother you with those, but we do them in wildlife, energy, health, and all different topics where we think we can make the world a better place using AI. This is then all real world challenges. And that means that this is also a way to do challenge-based learning and peer-to-peer learning within the global community. In this way, we hope to educate people about how to use AI in practice and also help organizations around the whole world by implementing AI for good. So today, this challenge has been a collaboration with several organizations. First but foremost, Space Hubs Network. I'll ask Simon in a sec to introduce this shortly, the organization that was so kind to sponsor this challenge. Then we have Vortex.io, who provided the Floods Challenge, Xomnia, who provided a team of their data scientists to tackle this flood challenge, and then Baltic State Service and Forest Radar Project, where Ilse is in charge, and they have provided the second challenge, the Forest Health one. But let me start off by asking Simon if he can do a brief introduction of why, what Space Hub Network does and why you sponsored the challenge.
Okay, yeah, thanks, Sago. Thanks very much. Yeah, quite simply, the Space Hubs Network is a project that's bringing together about 50 different space startups. We provide support for them if they're just starting, or we help them get experience defining the product. And for those space companies working further downstream with applications, we help them get funding for those projects. And so the reason why we wanted Footprints involved in this challenge was to find new companies. It's as simple as that. It's to find potential startups, and hopefully the companies will be created from this event. I'll post through the chat a place for you to apply online for free funding and free mentoring for your space project. So that's very simply why we wanted to get involved and why we've been watching this with interest. So thank you, Sako.
Very cool. Thanks, Simon. And thanks again for being involved in this challenge. Which brings us to Jean-Christophe from Vortex, if you can give a short introduction.
Yeah, thanks a lot. First, I want to thank you all the consortium to be involved in this challenge, because it was very interesting. We are focused mainly on the inland waters challenge and providing prediction on rivers floods. So it was very interesting to follow all the two teams that work on our challenge and see what the amazing results they have. So thanks a lot for that. And Vortex.io is a company dedicated to the monitoring of rivers, thanks to in-situ station that we installed and the dissemination of this data on our web platform. And so having the results from this challenge is very interesting for us in the future to provide interesting and forthcoming services from this data. So thanks a lot.
Awesome. Thanks, Christoph. And I'm eager to see the results, and then also, of course, how you will implement that in your platform and actually help organizations out by preparing for inland flooding. Then last but not least, I would like Baltic Satellite Service. I don't think that Ilse is here, but her colleague is here, I believe.
Yes, hi there.
Hey.
All right, so it looks like that with the forest health, it did not, so it was quite a challenge to go through all these data, and actually, yes, we didn't have any ready solution for this, so it's always hard to work when you don't know if it's actually possible to get any results from this data. So I understand this. I also worked like that in some projects, so I can understand frustration, but it also brings a lot of when you work in this environment, challenging environment, you also learn a lot from this. So hopefully all the participants there also got some new knowledge and new insights into how can operate with geospatial data and with satellite data in specific. So.
Yeah, indeed. The forest health was a very challenging one. Detecting excess water in forest is a lot harder than just detecting water. But I'm very curious with what the final research and say is on this topic from the team. But we'll have to wait a bit more before we are there, because over this time we actually did quite an impressive job together, because we had 10 weeks of hard work in 3 different groups. 16 engineers, but over 1,200 hours of engineering work was collected in this project. So, well, a little applause for all of you already, just based on that you all wanted to put your personal time in this project to help make the world a better place. So at least we at Footprints are very proud of you, and I hope you guys are also proud of yourself. But let's then first also see like what all these engineering hours and all this hard work resulted in. So as mentioned, 2 projects today, just to briefly recap. We had the AI for inland flood prediction. There, the goal is to develop models that predict flash floods, and also mainly like how the water will evolve downstream. And then for the forest health group, they build a model to detect excess water, or they have attempted to build a model to detect excess water based on satellite data. And I've seen many different pretty pictures, and I'm also curious to see how this resulted into the final presentation. But just to give everybody an insight on how they worked, how the teams worked, is we kicked off the challenge on the 20th of June, and then they started doing research and, hey, what would be the possibilities and what would be the different types of models and data engineering needed? How does the data look? Do we have sufficient data? All these types of analysis is a very important part of the whole data science process, something also often overlooked in many other projects, because the data sets are, well, maybe you could say over-prepared, at least for educational purposes. So they got their hands dirty right from the start, and then in the midterm presentation, everybody presented on the goals that they had for this challenge and the different things that they were going to try throughout the challenge, then working towards implementation. And right now, we are on the 22nd of August with the final presentation. So I'm just as curious as you guys are, but let me not take any more of the time. I would love to ask for the first team of the flood challenge to start their presentation.
Okay, so yeah, hello everyone. I am Pavlos, and I will be representing Team 1 for the inland flood challenge. Here you can meet the team. We have Agustin, George, Kiki, myself, Sabrina, and Samantha. What is this? Okay. So yeah, we all joined Xomnia on 2022. Most of us are machine learning engineers and data engineers with a passion for AI, and we decided to join forces in order to contribute positively to the AI community, and in this case, hopefully to the French people as well. So the approach, now we'll talk about the approach that we took. I will cover the features, pre-processing, models, and the metrics that we used. So regarding the features, the data was sensor data that measured the water level of the river across multiple stations. In addition, we also had weather data, like how much it rained on specific days and the direction of the wind, etc. But after talking with Vortex, we decided to only keep the sensor data, because that way we would make the model more, it could be more easily reproduced to other rivers of the world as well. So for the features we chose, we have the water level across all of the river. Moving on to the pre-processing, we had data from Vortex, which most of the time series data had a time frequency of 1 hour, but in some cases it had 30 minutes, 45 minutes. It was a little bit all over the place. We also had data from Wikicrew, which the main time frequency was 5 minutes, but again, they had 15 minutes, 10 minutes. It was also all over the place, probably due to missing values. And what we did to tackle this issue was to resample the data into 1 hour. That way we could use all of the data. We could use all of the data from both of the organizations. So after we resampled the data, we still had some missing values, which then we just use the interpolation in order to impute them. So we split up the group in order to build many models. Each one of us wanted to implement their own model, and that's what we did from the beginning. In the end, the 3 models that performed the best were the following: LSTM, ARIMA, and Prophet. So why we chose LSTM? It's widely used in research, especially for this problem, for predicting flood. It's all over the place. It's basically a recurrent neural network that's very famous for its good performance with time series data. The way we prepared the data for this was a typical supervised learning approach, split the data into train set and test set. ARIMA is a simple, probably everyone knows this. It's a classic time series method. It's a simple univariate linear model that predicts trends. It's an autoregression, differentiation, and moving average model. So for this model, the way we fit it is that we fit it using a week worth of data in order to forecast X hours ahead into the future. And then we shift the fit window by 1 hour and repeat this process until we have forecasted all of the data. The final model is Prophet. Now this is there's a big fuss around it, and for a good reason. It's a very good model. It's a nonlinear univariate model, but there is a trick to make it work for multivariate time series as well. I'm not gonna go more deep into it, into Prophet. Flin from the other team will go into more details. The metrics we used for evaluating our models were the root mean squared error, the mean average error, the mean average percentage error, and the correlation. The correlation is good because you can, although it doesn't give you a lot of insight in terms of how good the model is. You can see how good are the predictions, how good are against the small peaks, how good the model can predict the smaller peaks as well. So it's not very useful, but it's good to look at as well. Okay, so moving on to the so-called battle of the models. So once we had our models, first the best models that we kept in the end were the LSTM and ARIMA. So in order to evaluate them, we handpicked 2 stations. It was Marmande and Toulouse, and then we separated them into many train sets and test sets. Here you can see a visual representation of what I'm talking about. So this is for the station of Marmande. We created 3 evaluation test methods. So the first one was the orange part you see, the green one and the red one. And the training was the blue lines. If, for example, if we want to test on the green line, we were also allowed to use the orange line in our training set. And this is the same applies for the red part. And small spoiler alert, the model that performed best, surprisingly, was the ARIMA model, and the second one was LSTM, which hurts a little bit because I was the one with another guy who worked on the LSTM model, but it is what it is. It's always nice to see simpler models outperforming deep learning methods. Here are the results. So the results you see here are for the red part here, for the final experiment. They are for the station of Marmande, and they are for 6 hours. 6 hours into the future forecast. ARIMA is univariate, which means that we fit it with Marmande data, and we also forecast Marmande data. The LSTM, we built it into a multivariate fashion, which means that if we want to predict, we want to forecast Marmande, we used as futures all of the upstream stations as well. So we use Marmande and every station upstream, almost every station, not exactly all of the stations. And yeah, so the ARIMA outperformed the LSTM almost in every case. You can see that the mean average, the mean absolute error of ARIMA is 0.09, while the LSTM one is 0.12. The root mean squared error of ARIMA is 0.12, while the LSTM is 0.14. Yeah, we also had other results, but we decided to keep it short due to the limited amount of time. But in all of the cases, ARIMA performed slightly better. Okay, now I can show you a little bit, a small demo of the notebook. Let me go here. Okay, so here is the final notebook that we will deliver. We put everything into one notebook as requested by Vortex to make it simpler to look at and run. So here we just import every library. Because the ARIMA model is univariate, the way we prepare the data here is we only load the station that we want to predict. So here we only load the station for Blagnac. Here we set the some constants, like how many hours ahead we want to predict and how many days to use in order to fit the model. Here are the data preprocessing functions. In this method, we preprocess in order to only keep the height. Here we use interpolation, and here we use resampling. In addition, we include the methods for training the model and forecasting, as well as plotting the results, which are right here. And finally, we just simply run this pipeline, and we get the 6-hour prediction. A 6-hour forecast for ARIMA. In order to get these results here, you would have to repeat this process for every window. For example, you fit it a week, forecast 6 hours, then shift it 1 hour, and repeat this process all over again in order to get this the left graph you see here. So what are the next steps? Since ARIMA performed surprisingly well, of course, the next step would be to improve ARIMA and also utilize the data from other stations, because we have all of this data, but ARIMA only uses the data for one station. So one way to do that is ARIMA X or SARIMA X, which is basically it's implementation of ARIMA that also works for multivariate time series, and this is certainly will give better results. We are not sure how much better, but it will give better results. And another future step is to implement the model, deploy the model on the cloud. How you could do that is that, well, like you have when you deploy the model, then you would have live notifications to Vortex people, and then it will notify them in case the forecast is above a threshold, above a safe threshold, and then the Vortex people could evaluate more this forecast, and then they could act accordingly, like let their users know, for example. That's all. That will be the presentation. Do you have any questions?
Anyone, any questions for the first team? I already saw the results, so I already asked all my questions.
Yeah,
just a question, Pavlos, Simon.
Mm-hmm.
Did you have enough time within the time available? And if not, what would you have done if you had a bit of extra time?
The time was enough. Yeah, of course, we could always do more, right? So in terms of doing more, like implementing the ARIMA X, for example, we didn't have time, but we had enough time to implement ARIMA and LSTM at a satisfactory level. Now, if we had more time we would implement, of course, ARIMA X or SARIMA X. And from the LSTM part, we had some ideas, but we didn't have time to implement them. So, for example, for the LSTM part, we we also included futures, additional futures that would that were basically 0 or 1, and they were anomaly detection futures. And we did a little bit. We ran some tests, and the results were not much better. They were not very apparent, but these futures were actually we had a future importance method, and they were highly important futures, the ones we added. So we believe that there was potential there, but yeah, we needed to run many more experiments and hyperparameter optimizations, and how many futures to keep, how many of the upstream stations. So yeah, we didn't have time for that, unfortunately, but that's what we will do from the LSTM part as well.
Okay, thanks.
Yeah.
And just one question, quick, because I already saw the results also, as Sako said. Yes, I think that the great interest here is ARIMA X, because estimating or predicting the water level to a station using the upstream station is something that is the main goal, I would say. So why did you have enough time? Why you didn't have any time to test this solution? Because is it maybe the exploitation of the data that take a long time and prevent you to investigate the ARIMA X solution?
Yeah, so this was basically completely because of we also have clients. So the people who were working on the ARIMA X found a client, so they didn't have a lot of time. Sorry, the ARIMA, not ARIMA X. So they didn't have a lot of time to explore it more. But it was also like 2 weeks. So yeah, it wouldn't. It was only for a time manner. We did the person who did this actually implemented ARIMA X, and we got some preliminary results. We didn't run out of experiments. That's why we didn't put them here. These preliminary results actually showed some small improvement from the ARIMA, but yeah, we didn't have time to further advance it. But already the first results show that it's better, and that's the way to go for sure.
Yeah,
oh, thanks.
So if I understood from Augustine, who I think did try ARIMA X, it was very slightly better, which might not even be worth the extra processing power that you would need to do it. Also in regard, of course, because we also have the second profit model, which ended up outperforming the ARIMA one. There was more time spent on finalizing the projects and the documentation instead of exploring this route that would only bring slight improvements.
Yeah.
In any case, I want to thank you, because the ARIMA works nice, and having a 6-hour prediction is something very valuable for inland floods. So I think it's already a good job. So thanks a lot.
Yeah, thank you.
Cool. Oh, if there are no further questions, then I would thank you for the presentation, Pavlos. And that brings us to Flin from the second team, who will present his results on the same challenge.
So just let me start by introducing the team. In the end, only 2 of us were left, sadly. Me and Sabello. This is one of the struggles that I will come back to, but it was so we managed to pull off a nice project. I think we managed to get some results that we're happy with. First, let me elaborate on how our project went, so our process. So initially, we started with 2 tracks in parallel. The members who were there initially but aren't here anymore, they started with the literature study, and I focused on the data cleaning and data analysis. And in the literature study, you look at how this is done in research, for example. After a while, you combine this with model selection. You come up with some criteria that are relevant for your model, such as we thought that it was important that the model was multivariate and that it could take in seasonalities, etc. And then afterwards, after you found one or multiple models, you prepare the data so that it works for the model, you train the model, evaluate the model, and then you just do this several times until you get some results that you're happy with. So as I already said, in our analysis, we found that our solution needs to be a model that can work with multivariate data, since we want to include the upstream sensors as well. And we also found that some stations that are more near the coast, they suffer from some seasonality because of the tidal forces that come into play. So I'll show some some plots later that will make this more clear. And we found several solutions, but our most promising one, and the one we use in the end, is Profit. It's a model developed by Facebook. And in the end, what it does is it tries to fit the signal. So the things that you're measuring, it does this by fitting a trend, fitting several seasonalities, fitting in events. So that makes more sense I thought this initially made more sense in business cases, for example, where you have a sale or something. That of course influences the results, but I'll come back to this later. And then you also, of course, have some error. But what we liked about this part is that it fits the trend and the seasonality, and it all just does this automatically. Now on some struggles that we had with our process is that initially we started with 5 people, and this dropped down to 4 and 3, and now we're just the 2 of us. And because of this, you cannot do all the things you set out to do. So initially we set out to explore some other models as well, such as the ARIMA that Group 1 mentioned, and FAR. With this, you would also need to do some further processing. But so we didn't get to look at those. Still, it would have been nice to try them. And additionally, you cannot generate or analyze results for all stations and see where the model breaks and see if you can improve it, which is sad, but I'm still very proud of what we managed to do. Now onto the results of. So we had 1 year of data. We trained our model on the first year of data, and then for the next 4 months we predicted. So the next 4 months is the test set, and we in this case I only showed the results for 24 hours into the future, because this was also the point where the performance of the first team started to break down, and we noticed that the Profit model still worked fairly well especially for the lower parts. It worked really well, and so for 8 hours or 2 hours into the future, it worked really well in my opinion. And we'll predict I'll show the results for 2 cities, for Marmont and Cadillac. I probably butchered that pronunciation, but sorry, Jean-Christophe. First, Marmont. So first, what you see here is just the measurements by the station in the test data. So I'm not showing the training data, just so that you can have a clearer view. On the x-axis, you see the date, and on the y-axis, you see the height of the water. These are the predictions if you only use a univariate model. So only forecast 24 hours into the future using only the measurements at Marmont itself. And yeah, this is nothing to be proud of, I think. But if you include the preceding stations, so that's MV, multivariate, then the results start to get much better already. Especially in the beginning of the test set, so when it's most near what the model knows, the performance is really well, but over time it starts to drift off. So for this reason, we also trained what I call multivariate plus. And what this is that I predict the next day, then I train a model on that day. I predict the next day, and I keep fitting the model with the new data as it increases or as the time goes on. And as you see, this really improves the performance of the model. And in fact, in practice, the model would be even better, because then you could just train the model on all the training data and all the testing data and just make the one prediction. But this would have taken too long to do it for the entire plot. So now I just refitted the model instead of retraining it from scratch. Another nice thing about the Profit model is that it can also give some error bound. So this is the 50% confidence bound that it gives. And yeah, so now in most cases, at least the confidence bounds envelop the actual measurements, but in some cases it doesn't. And these are, for example, some flood events, or not sure if they're actual floodings, but at least the water height rises rapidly. So you want the predictions to be accurate at those points, but there's a mismatch of a couple hours, which is significant, as Jean-Christophe said. What I think would be a solution for this is to try to include the events. So if I go back to the description of the model, here you have these events that you can include. They're like binary indicators, like, oh, this event happens. And maybe what would improve the performance, I think, would to make some custom events and see if they help. For example, it's been raining for 3 days in a row. That's an event. We call it a rain flooding event, and I think that would help with improving the performance, especially with those flooding events, with those nasty peaks. Yeah, those were the results for Marmont. Now I want to go over to Cadillac. The problem with this is that it's more of a coastal city, and with the coastal city you have more of those oscillations. So you have the daily oscillations. I think they are from the day-night cycle, I think, and then you have this longer scale oscillation. I think it's from the like the full moon cycle. I'm not sure if that's true. Again, if you start with the univariate, it's nice that it tries to do something with the seasonality, but it doesn't get it right. If you introduce the multivariate, it starts to get much better, but still not as good as I would expect or would have hoped. And also here, if I do the multivariate plus, so if I refit the model after every prediction step, the performance doesn't increase too much. My explanations for this are twofold. So as you saw with Marmont, the multivariate plus model works best as you get further away from the training data, but this isn't the case. So this is only a month of data approximately after the training data. So the deviations haven't started to stack up yet. What I think is the problem is that Prophet assumes some base seasonalities where it looks at, for example, are there some seasonalities within a year or within a month or within a week? And I think if you do some fine tuning there, for example, find a seasonality every 12 hours or something, then you would improve the performance as well. Now, based on our projects and everything that I've said, here are the lessons for the key takeaways for our team. So data cleaning takes time. This was a big hurdle we bumped into, like Zach already said. But yeah, I think 3 weeks or something is a good, would have been a realistic guess for the data we were provided. I was really surprised by how well Prophet works, for how simple it is to use. Yeah, so I'll use, I think this will be my go-to for new time series models. And I come from, I still study at university, and here everything is deep learning, at least in the electrical engineering faculty. And this was my instinct as well, to just try to use an LSTM. But I think it's very interesting to see that this isn't always the answer. So nice lesson for me. And regarding the last lesson, so emphasize attendance for online projects. This is about why I think our group crumbled. So we had people from lots of different time zones, and for them it's really difficult to attend either the weekly meeting or the sub-team meeting. And I think if you can't attend both, then you're just not, even despite how enthusiastic you might have been in the beginning, you will just lose your interest because you can't be there and you always need to catch up. And I think for my lesson personally for the next time I do a global project like this, or with people from lots of different time zones, is to really try to find a time zone that works for everybody, so that everybody stays engaged. Because I think that we would have been able to put down a much better project. So then, based on all this, some recommendations for Vortex. Yeah, I would try to train the Prophet on multiple years of data. So you provided 2 years of data, but I didn't get around to doing that, to training on it. For the coastal city, explore different seasonality parameters. So what I said about why I think the predictions for Cadillac are bad, and try to find some preliminary, some binary events that you can use to increase the predictions for flood events. I think that would also help. That's it for me. So if you have any questions, please shoot away.
Thanks, Flin, for the presentation, and also thanks for the feedback on the process. We will also be sending everyone feedback forms so we can collect this and improve the process, and hope the next group doesn't crumble as far down. But very impressive. Thank you for taking this through and getting these very impressive results as well. Also, I can reiterate for everybody here the lessons that you've mentioned. I've also seen in previous forecasting projects that actually both ARIMA and Prophet often outperform very complex recurrent neural network-based solutions. So I guess that's a lesson I can only underline for everybody in the call, that for their next project, start with the simple ones, because they might keep outperforming the complex ones for the upcoming time. So thanks. Any questions for Flin and his team?
Yes, a few questions. So first, I want to thank you, because finishing the project with only 2 people is a kind of challenge. So thanks a lot, and the outlines are very interesting. Just one question: when you mentioned the MV plus model, so the multivariate plus, what does mean the plus?
Yeah, so I will go to one. So how I train the model is that the first 8 months are training data, and the next 4 months are testing data. And initially, as you can see, in the beginning for the regular multivariate, it performs well, but over time it starts to drift off, because I think this is because it hasn't been updated with the most recent information. So with the plus, what I mean there is that every time I forecast one step in the future, then I fit the model. So I update the model with the information that you would have gotten there in practice, and then I do that again. So again one forecast in the future, and then re-update it. And in practice, you could do this. So this is probably what if you were to use this model, if you were to deploy it in the real world, you can just retrain the model every day.
Yeah, just to add on terminology there, as I'm familiar, this is called a rolling prediction model. So you roll over the different time frames that come in. So if you want to Google it or whatever, then that's probably the best.
Wasn't aware.
What time window did you use for refitting it?
So what was your question?
What did you use any time window to refit it, or you just use all of the previous data?
No, so the profit model, you can like warm start it with the parameters that you would have gotten with how you trained it the previous step. So you already have the model from the previous step, and you train a new model, but you started with the parameters from the preceding step, and then it speeds up training like factor 5 or something.
Okay. But what about the data you fit to the next model? Is it like do you refit it like a day worth of data every time?
Yeah.
A day. Okay, cool.
Yeah, I think for now I even did like every hour. So I predict 24 hours into the future in 1 hour increments, and then I just predict 1 hour in the future, predict an additional hour, refit, predicts, refits.
Okay, yes, I get it. Thank you.
Any other question for Flin? If not, then for now, a final thanks to you, Flin, and your team. But we'll be proceeding quickly to the forest health group as well. For that, I would love to give Julieta the room. See what you guys came up with.
Okay, so I will be talking about the second part of this challenge, which is the AI for Forest Health Challenge. First, meet our amazing team. We are Mohammed, Anayas, myself, Julieta, team, and Dipali, and we've been working together for these past few weeks and months. Okay, so we started the challenge. We were presented with a general problem that was that the presence of too much water for an extended period of time would damage the forest. So considering this general problem, we could think and ask ourselves different questions and see if we could answer any of the questions. So we could think about how to detect excess water without delay, how to quickly find beaver dams that are one of the reasons that the forest can get flooded, how to recognize water on the tree crowns, how to detect excess soil moisture, accumulation from heavy rains, and how to get accurate data to provide to forest owners. And to try to answer any of these questions and to target this problem, we were given a lot of data. We have very different types of data. We had vector data that consisted in our area of interest, that there were 2 regions in Latvia. We had a field data with detected excess water. So basically we had polygons around the floodings. We had data from different forest research institutes, like we had water, beaver dams, and excess soil moisture. We had images from Sentinel-1 and Sentinel-2, soil moisture, groundwater, LiDAR data, orthophoto images, state forest register information, and meteorological data. And so we decided to put our objective as using a machine learning approach to correctly classify flooded areas in aerial images. And this is because we had a lot of different types of data, and because of the time we needed to focus on certain types of those data, we couldn't use all of it. So we decided to focus on the vector data. Here you can see the type of data we had from the vectors. We have 2 areas in Latvia. two areas in Latvia. We had one that was the Saldus region and the Kalsnava region. The Saldus being a lot larger than the Kalsnava region. You can see it delimited here by the purple rectangle, and then you can see different tiles. And what you can see in blue are the flooded areas. If we zoom in a little bit more, we can see that here the floodings are like small polygons around exactly that area that was flooded. And if you zoom in a little bit more, you can see that we have different polygons stacked on top of each other. That is because we have data from different years. So what we did then was to separate all of those data from the different years. So then we could match that with the images corresponding to those specific years. And so we talked about, we use the vector data, and the other type of data we use is the raster data, the images, right? So we used images from the Sentinel-1 and Sentinel-2 that are satellite images. They both have a resolution of about 10 meters. And the Sentinel-1 gets radar-like images. So it scans the surface and it gets images from either day and night and in any type of weather condition, because it goes through the clouds, so you don't have any type of problem with the clouds. With the Sentinel-2, that doesn't happen because it takes pictures of the surface. So we can have a lot of problems with the clouds. Here you can see like the natural color. This is one of the good pictures, but we could have many different problems when downloading these images. And we also have the orthophoto images that are obtained with a device that goes a lot closer to the surface. So it doesn't have any cloud problems, and the resolution is a lot better for about 40 to 15 centimeters. And here you can see that it has a near-infrared filter that we use later on because it's better for finding healthy vegetation. So for the Sentinel images, we used Sentinel Hub, which we could use as a plugin of the QGIS, and it made it really easy for us to download the images for the specific coordinates we had, and for the specific times. We could easily download for year and month, actually. And so this is what I was referring to when it came to the Sentinel-2 images. We could have images with many clouds. This, of course, we cannot use, and with a lot of snow. So this type of images were discarded, and we only kept the very clear images. Then this is what I was talking about when I referred to overlapping the vector and the images. Here we have like one of the Sentinel-2 images, and then we can put on top of that the flooding areas for that specific year that picture was taken. And from that, we could get the masks of those images, and we were going to use to train our models, right? And these are the orthophoto images that are RGB2, but like I said, they have a better resolution that makes them a lot heavier for us to use. It was really hard because they were really large images. And what we did, here you can see the Saldus region. What we did was we only kept the tiles of that area that contained flooded parts, right? So that way we could make sure that the data set was a little bit more balanced and that it wasn't so heavy for us to use and download and everything and process. And so this is one of the reasons we use infrared images. The near-infrared band is very useful to find damage and healthy vegetation. So here we can see, like, this is an example for a 2013 that we can see that the damage plots have a lot of more percentage of the near-infrared band. So it can like easily differentiate the damage area and the forest area. Here is a little bit more, they are more alike, but maybe because this was taken during spring, so it was harder to make that difference, right? So here is another example of the orthophoto images. Here is the forest contour, and inside that forest we have the flooded areas. This is very useful because we actually want to detect the flooding only inside the forest and not outside of it. So it's important to make this distinction and to make sure where the forest is. And here you can see a close-up with the infrared filter and another damage plots. So with all of these images, we tried different approaches. So I'm going to show you some of the results. So we started with an XGBoost, with a classical machine learning algorithm that we know it's not ideal for image analysis because it goes pixel by pixel. But actually, it was good for us to use as a benchmark because we could see how well it classified each of the pixels as flooded or non-flooded. So we used the XGBoost on the Sentinel-2 images, and the corresponding masks for the Southwest region. So we performed the pixel-based classification, and we got an accuracy of about 66-67%. This we have a confusion matrix of the predicted and the true labels of the non-flooded and flooded areas. And yeah, it was better to correctly classify those areas, those pixels. And then we started working with the units, which is a fully convolutional neural network that has two parts, an encoder and a decoder. And this performs semantic segmentation that we're going to use for pixel-wise classification because we didn't want to make a classification for the entire image. We wanted to create a mask that segmented our image and from there classify those different segments. So when we tried that unit on the Sentinel-2, we got an overlap between the actual and the predicted damage areas of 71%. It was better than the XGBoost, so that was great. But then when we tried the unit on the Sentinel-1 and the orthophoto images, the performance went down a lot. So we're not completely sure what this happened. Here you can see the damage area and the predicted damage area. They look pretty similar, but overall the performance was not so good. The same thing for the orthophoto images. And one of the ideas we had from training this unit, as you can see the orthophoto image, like I said, the resolution was a lot better than the Sentinel images. So we realized that, we had to cut the images in images of 224 by 224. And if each pixel has 40 centimeters, we were only getting like about 90 meters squared of the surface. And it was kind of like very zoomed in. We weren't getting a large image of the surface. So we felt that maybe that could be one of the things that was making it hard for the units to work. Maybe it was hard to make a mask when most of the image had one type of forest. Here you can see one of the images that is really really zoomed in, and the mask that contained mostly damaged forest, right? So what we did here was to perform perform classification with a regular CNN and using the images as damaged and healthy. Damaged if they contained any type of damaged forest or flooded forest, and healthy if they didn't. And we tried a regular classification with an inception before. And we actually found that the classification accuracy was a lot better than with the units. It was about 74%. Here you can see as well the confusion matrix. The data set was pretty balanced, but it didn't have many images. So that could be something to try next. And yeah, these are most of the results we got from this type of analysis. And going through something a little bit different, we did a flood mapping on the Southwest region using Sentinel-1 data. So like I said, some of the advantages of using Sentinel-1 data is that it can penetrate through clouds and it can capture data day and night. Has a 10-meter spatial resolution and a 6 to 12-day temporal resolution. This was done with Google Earth Engine. And so what we did was we used the BH band that is used for flood detection normally. And we looked for specific flooding events in time. And we got pictures from before and after that flooding event. If you can see here, the after image of the flooding, it's a bit darker in certain spots than the before. And here we passed a speckle filter. And then we used a threshold for this channel that can measure flooding. And this is an initial threshold of 1.25. And then we took from that, we removed the permanent water bodies, and then we used a slope mask to remove this, the terrain that had a slope larger than 5 degrees, because water would normally accumulate on that. And all of that we removed from the initial threshold. And from that, we got like a mask that could tell us that what you can see here in red, the flooded areas. And we thought this could be eventually useful to creating masks for areas that we didn't have already targeted as flooded. We only had those type of masks for certain regions. Maybe we could try to work on different on regions that are not delimited here, and maybe we could try to use this and create masks, for example. That could be one of the uses. And yeah, we got the total district area from for Saldus and the flooded area for that. And okay, these are all the results I had to show to you today. And these are some of the final thoughts. And of course, like many other team members said, the pre-processing of the images is the most challenging and time-consuming task. We used most of our time in this challenge pre-processing the images and selecting the data we were going to use, making sure it was useful and that we knew how to handle that data. And from that, the idea to get that could be used in the future is using channels that recognize water, like the Sentinel-1, or damaged vegetation at the near-infrared band, and that could be very useful for the classification. And then making sure that we train the algorithms with only flooded forests and not any type of flooded terrain, making sure we're not using permanent water bodies. And then using meteorological data, of course, and LiDAR, like the 3D model of the terrain, that will, of course, be useful as well. And so this is all I have to show to you today.
Awesome. Thanks, Julieta.
Thank you so much.
Results, and I'm very impressed as well with the final things that you came up with in the last week as well. Especially, if I understood it correctly, that might be a question as well. The last analysis that you showed, it's basically an unsupervised way to find flooding in forest, right?
Yes.
Were you able to like validate the accuracy of that in a way?
No, that was the last thing we did, like in the final few days. So we didn't check what we got there with the actual mask of the flooded, but yeah, that could be very useful as well.
Oh yeah, no, that's very, very interesting. This is, of course, a very useful direction because you could use it all around the globe, basically, which makes it very scalable compared to the models that will be trained on only, in this case, Latvian soil, and would probably not generalize too well. And also, like the 71% overlap between the masks, that's also definitely not bad. So for a problem this hard, again, reiterating for everybody, we're trying to detect moist soil, basically, so not like clear water plains, but and some of those are still under like canopies. So
under the forest, yeah, exactly.
Under the forest, so this was definitely a very hard problem, and we're not certain that we could get decent results on this at all. And I think you just proved that you can definitely do this detection. So with improving these directions that you took, I think there's actually a serious chance that this problem can be solved completely. So I also hope that Baltic Satellite Service is able to use the insights that you gathered to finalize this project on their side as well. Maybe Andrei, some words from your side on this.
Yeah, of course. I think it's awesome that you got these results from. So I think it was really challenging and not enough time really to dig in to all of this. I work with this every day, so I understand how hard it is to process all these data and trying to combine all these in many dimensions, because it's also the spatial dimension, the like different sensors, and also the time dimension. You need to stitch together the years or the months or seasons for vegetation. So it's really hard. So I think it's awesome that you got where you got, and you got also some insight into this. Hopefully it will help you in your future work or research, and you'll get some head start if you have something like this in the future. I also had some questions regarding, you said that you used a balanced data set. So was it the same data set for all the data sources, Sentinel-1, Sentinel-2, and orthophoto?
No, the balanced data set I was referring specifically was when we used the inception before on the orthophoto images.
Okay.
Because that's how we put on the data set itself. We had the same amount of damage images and healthy images. But yeah, most of the time, we tried to make them as balanced as we could, but sometimes that wasn't the case.
Yeah. Okay. So yeah, I think it's important to understand the accuracy if you use a balanced data set, and then you can really estimate. Another thing, I really did not get which bands did you use from Sentinel-2, for example, because the useful bands for vegetation and for water mapping and useful indexes like NDVI and NDWI, which could be used, they could be pre-calculated from the bands and then used in a model, or you could use a model directly on these bands, which are useful for these indexes. So I'm not sure about that. If you used all the bands or just some?
No, yeah, for the Sentinel-2 images, we use the RGB bands from the natural color images and not the NDVI yet. Yeah.
Okay, so yeah, actually for vegetation and water, the near-infrared band is useful, and SWIR, super wide infrared, I think. So these bands are very useful for vegetation and water. And so, yeah, I know a lot of researchers, they just put everything in the model straight away. They do not try to classify, and they just put all the, I think, 11 bands there, and so make the model to understand what's useful and what's not. And sometimes if they have time and they want to compress the model, or they can just try to pick out the separate bands and see how it influences the accuracy. But from for a rough start, it's, I think, a good practice to just put everything together.
Great.
And same goes with orthophoto. So there is actually there were like RGB orthophoto and infrared orthophoto. So actually there are 4 bands, RGB plus infrared. And by combining these 2 images, you can get all these 4 bands for classification. But it also takes some calculation and preparation before you can use it inside. So not very straightforward in this way. Also, it's a good practice to use like high resolution data from the start to try to get some trends from the data. For example, if we have high accuracy from the orthophoto or from LiDAR regarding classification, then, but you do not have a lot of data in this way. You have, for example, just 1 year. But you can train the model on this, and you can see some trends, and then you can extrapolate on the satellite data, for which you can have much more temporally. You can have much more data points, and you can learn how you can classify the satellite data from the more high resolution data, and like gather more ground truth data in this way. So I hope it makes some sense what I just told. Yeah. So yeah, I think it's great that you got where you went and got with this data, and so good luck with your future work, and if you decide to work on the spatial data.
Great, thank you, Andre.
All right.
Awesome, thanks, Andre, for the additional insights as well here. Are there any other questions for the Forest Health team? I don't see any hands raised. I think that then concludes the presentations. So for then some final words from my side. Well, of course, again, I guess I've said it a bunch of times already, but thank you to all the participants to spending your time on this project. For me personally, it's always a bit of a fuzzy feeling when I go into these challenges, because I see like how so many people put their efforts towards one goal and actually try to make a real impact and help out, make the world a bit better. Also, we will be open sourcing these results such that not only the organizations that we got the challenges from will be able to use your insights, but also other projects that do similar, use similar data. I thought it was very interesting once more to see that even if you get this different type of data, right, on the one side, multispectral satellite data, you need to keep into account, it's not just images, you also have all the different coordinates and over RGB bands. And on the other side, relatively simple signal data, both have the same problem. The pre-processing takes the most time. And this is why you do AI in practice and not just do like simple assignments, which you often get at university. This is a very important part of the data science field. And I hope that you guys have learned a lot from doing this challenge. And also, I hope that we can make some real impact by getting it implemented. And I think that especially also in the case of the flood teams, that there will be some serious impact based on your performance. So once more, thank you all for the time, effort, love that you poured into this project. I at least am very proud of you. And if you are not on yourself, then this again is a way, is for me to make sure to hope that you are also very proud of the results that you gained throughout, even if there were some struggles, you all got through them. So thank you all once more. That leaves, for me, that's it. If anyone wants to give a final word as well, this is your moment to shine.
Yeah, just thanks to everybody. Thanks to everyone. And you can see in the chat, Julieta, Pavlos, Flin, there is the address to look at the Space Hubs network. And you can have a look at how we can help you if you want to go further. And great, good work, hard work. And of course, it's difficult because nothing that's easy is worth doing, okay? That's my final word.
Okay, guys, then I will be rounding off the presentation. Thanks once more, and for all of you, have a very, very fruitful day.
Thanks, everyone.
Great, thank you.
Thank you.
Bye.
Bye-bye.
Bye, everyone.
Thanks, guys.
Thank you to all of you. Bye.
Cheers.